Okay, hello compaction class. This is your second lesson of the day. This one's going to be a lot faster. I'm just going to kind of talk through it a little bit. Here's 6.1.3. How can I describe it? It says describing transformations. It's basically looking at something that has been transformed. Okay, so in this case it goes from ABCD, quadrilateral ABCD, to quadrilateral WXYZ. And how did the coordinates of the point change? So you just got to describe the transformation. So all you really need to do is just figure out the corresponding vertices here, like A goes with W, and then figure out how did it get there. So this you could see doesn't look like a rotation. It's still oriented the same way. Doesn't look like a reflection. It looks like a translation. So all you got to do is count how far did A go to get to W. So if you look to the right, 1, 2, 3, 4, 5, 6 to the right, and 1, 2, 3, 4, 5, 6, 7, 8 up. So that goes 6 to the right and 8 up. And I just went to a screen I did not mean to go to. Ooh, that's fun. Live recording, not live in classroom, but I'm only doing one take again. So anyway, we're just trying to describe the transformation. So that would be a transformation of 6 right, 8 up, or if we were to put it in coordinate form, it would be x plus 6, y plus 8. What I want to do now is I want to go to my notability, and I'm going to give you my own little definitions of the 3 transformations we've learned so far. If you don't like mine, you can, of course, use the book's definitions, which are sometimes a little short, a little sweet, maybe sweeter than mine. So they're right here. Translation, you can see it's slides an object horizontally, side to side, vertically, up or down, or both. A reflection flips an object across a line called a line of reflection. A rotation turns an object about a point. So here's my definitions. I'm going to go to my notability here, and you can see I put the same math notes box there. But up here, a translation is a move left, right, up, or down of a geometric figure on the coordinate plane. Also, again, notice I'm reiterating that rigid transformations maintain congruence. That was something I had just mentioned. So that means they have the same size and same shape. So on this example here of a translation, if we go from A to B, you can see triangle A over to triangle B, we went x plus 4, y plus 1. That just means you take the coordinates, you add 4 to the x, 1 to the y, and you'll end up with the triangle being in position B there. Okay, what about a reflection? A figure flipped over a line so that all points on the corresponding figure are equidistant from the line. So basically, when I say corresponding, that means this vertice corresponds to this one here. They are both the same distance from that line of reflection, in this case the y-axis. They're both one space away. And you can pick any point along this and its corresponding point over here on the other hypotenuse of that other triangle. Those will be the exact same distance from the line of reflection. The 2 most common lines to reflect figures across are the x-axis and the y-axis. So one nice little thing to note about a reflection across the x-axis or the y-axis is this little bit right here. So if you start with xy and you reflect across the y-axis, you will end up with negative xy. So let's take a look at that on this example over here. So what are the coordinates of this vertice? -1, +2. And its reflected point is this one over here. What are its coordinates? 1, 2. So how did it change? All we did was change the sign of the x coordinate. And that's what we have going on up here. From xy, it goes to negative xy. You just changed the sign. Then the same would be the case if you reflected across the x-axis. You just change the sign of the y coordinate. So that's how you do a reflection. And then here, a rotation. These are the hardest ones. And again, I'm going to have to spend some time in person with you guys on how to show you my little technique for doing this. But basically, if we're going from triangle A in quadrant 1 here, the quadrants go 1, 2, 3, 4, like making a C. That's how you remember how the quadrants go, like that. So triangle A is in quadrant 1. We're going to rotate it counterclockwise 90 degrees about the origin. Now, the last time we did a rotation, it was about a point that was one of the vertices of the triangle. Well, this time it's about the origin. Well, what does that mean? That means that if I were to take any one of the vertices of this triangle and draw a line to the origin like that, okay, I would then have to make a 90-degree angle to figure out where the other one goes. And so this is the rotated figure here. Okay, and I don't know why it's not straightening. There it goes. So this makes a 90-degree angle right there. And this corresponding vertice and this one right here, that's a 90-degree counterclockwise rotation. Now, how can we practically do that? I have a little way of doing this. My way of doing it is to figure out the coordinates of the vertices of triangle A. Notice I've got 2, 1 here. And then I just think to myself, okay, if I'm going to rotate this 90 degrees counterclockwise, what I can then do is just rotate my paper the reverse direction and put in coordinates of that exact same point. So if the coordinates are 2, 1, and I were to rotate my paper instead of counterclockwise 90 degrees, I rotate it clockwise 90 degrees and pretend my x-axis is actually up here now. Now, this is the part that's hard for me to describe on a video like this. What I might do maybe is turn on my orientation lock here on this so that when I rotate this, this is me now rotating this vertically clockwise 90 degrees. And now I'm thinking in my head that this is the x-axis and this is the y-axis in my head. It's not really, so I'm just kind of thinking like that. And then I'm thinking, okay, well, what point was I going to put in? I was going to put in a point at 2, 1. So if you're turning your heads with me in order to be able to see this, I don't know if you can. Maybe it's better if I turn off the orientation lock, and if I rotate it vertically like this, whoop, there it goes. So I'm not sure how this will show up on the video, but then I go to point 2 on my new x and 1 on my new y, and it shows up right there. It's a little confusing probably as I talk through this here, but that's one way to go about it. Some people are just good at visualizing where a 90-degree rotation would be. And I'm going to go over this again a little bit more with you when I get back into class. But if you also look at the coordinates, a 90-degree counterclockwise rotation does this. Notice what it does here is the 2, 1 becomes negative 1, 2. So we're essentially switching these guys around and then changing the sign of the y. As it moves to x, it'll change its sign. So you can see that 3, 1 became negative 1, 3. 2, 3 became negative 3, 2. Now, again, the rotating about the origin is also the most common type of rotation that you're going to come across. I know your book doesn't always do that, so it typically would rotate around a point that's already attached to it. But we need to get used to rotating about the origin. If you don't get it in the next few days, don't worry about it. I'm going to go over this again in person, and it'll make a ton more sense. So what is a rotation? It's a figure that's rotated about a given point and redrawn so that all corresponding points are equidistant from that given point. So every corresponding vertex will be exact same distance from the point that you're rotating about. and then you would also be able to draw an angle. So if it's 180 degrees, you draw a straight line. We typically only do 90 degrees clockwise or counterclockwise, and then 180 degrees. Anything other than that, it's just an overlap. So that's how I look at these three rigid transformations. What are you going to do today in the homework part here? I've actually got it loaded here, and you're supposed to try and figure out what happened. Like, these are each translations on part C. So how did they end up going from 3 to 5, or 3 negative 2 to 5 negative 9? What happened? Well, you just got to figure out, what did they do to the 3 to get to 5? Looks like they added 2. So that would be x plus 2 for the x part of it. And then the y, getting from negative 2 to negative 9, well, it looks like that went down 7. So you would write y minus 7. And that is the translation for that one. Okay, so that's that. Do your best with this. Your assignment for this one is 627 to 632. Both of these assignments, the 12 to 17 and the 27 to 32, are due at 9 a.m. 2 days from today.